Hello class, this is a continuation on calculus. In this video we will be looking at the applications of the derivative. When calculating the derivative of a function or a curve, we should not forget that the derivative is actually a function that calculates the gradients of any tangent at any point x1 along the curve. So for example here, the gradient of this tangent here at x1, so this is the point P, is calculated as, so the gradient of this tangent is the derivative of the function when we substitute x1, whatever that might be. A critical point important to calculus are stationary points. You can also call these horizontal tangents. The gradients of the shown tangents, these ones here in orange, this one here, and this one here, the gradients of those are 0. So hence there are stationary points at this point here. So if we were to find the derivative of this curve and substitute x1 into the derivative, it will become 0. Same goes for this one here. So let's do a few examples demonstrating this. So let's calculate the gradient of the function, this one here, at these different points here. So here we go. So to find the gradients of this function, we need the derivative f prime x equals 2x minus 6. So now if we want the gradients at x equals 0, we substitute 0 into the derivative. 2 times 0 minus 6, that's just minus 6. So the gradient at this point is negative 6. Same goes for this one. If we want the gradient at this point, f prime of x equals 2 times 4 minus 6. That's 8 minus 6. The gradient of the tangent at this point is 2. One more example. F prime of 3 is equal to, well, that's going to be 2 times 3 minus 6. Well, that's 6 take away 6. That's 0. So at x equals 3, there's actually a stationary point. So from the function, so we have this function here, calculate the gradient, calculate where the gradient of the tangent is 4, negative 6, or 0. So whenever we're actually asked to find the gradient of tangents, we immediately should go to find the derivative. So f prime of x is equal to, differentiating this expression, becomes 2x plus 8. Now reading the question very carefully now, it's saying that the gradient of the tangent is 4. So if we were to draw this, let's draw a real quick sketch of this. This is a parabola. It would look something kind of like this. So somewhere along this curve, there is a tangent. Let's say it's here. That tangent has a gradient of 4. Where the tangent is 4, what is the x value at that point? This is what the question is asking. So to do this, we're going to let this expression, because remember, this is the gradient. So we're going to let this expression equal the gradient we are looking for. Now, by solving for x, we will find the value of where the gradient is 4. So 2x equals negative 4, x equals negative 2. So in this really bad drawing that I've shown here, if this is the function at x equals -2, and if we draw a tangent at that point, the gradient of this tangent is 4. Illustrating this next question again, -6. So a gradient of -6 is very steep in the negative direction, so it will be like this. So wherever that hits, we're looking for the x value at this point. Once again, to do this, 2x plus 8 equals -6. Solving for x, we get 2x equals -14, x equals -7. So at this point here, x equals -7 will give me a tangent of -7. Sorry, of 6, -6. One more example here. So we want to find where along the x-axis will it give me a tangent of 0. So really we're looking for the stationary point. Oops. So we're really just looking for that point there. Well, to solve for this, we let 2x plus 8 equals 0. Solving for x, we get 2x equals -4, x equals -2. So that point there is x equals -2. Let's do one more example. Let's calculate the coordinates of any stationary points of the function f of x equals 1/4 x to the power of 4 minus 2x cubed plus 4x squared plus 5. So this is just a very quick sketch of the function. And when it asks us to find the stationary points, what we are really looking for are these turning points along here. Well, to find the x values for this, let's actually use the fact that these points have tangents that are 0 gradients. Well, when working with tangents, we actually need to find the first derivative, or just the derivative. So f prime of x equals, this becomes x cubed minus 6x squared plus 8x. So now we want to find values of x that will give us 0. Because remember, this is the gradient, and we're looking for stationary points here. So solving for x here, let's factor out x. Factoring this further, we get x brackets -2 and -4, which gives us the three solutions: x equals 0, x equals 2, and x equals 4. So the x coordinates of this are 0 something. X coordinate of this one is 2 something, and this one would be 4 something. Well, because we're looking for the coordinates, now that we have the x values, we can just use the original function to find the y values at those points. So f of 0, let's just copy this down. F of 0 Substituting 0 to all of these, that's just all zeros. That becomes 5. So this is clearly an incorrect graph, because it's supposedly 0, 5. So the function actually should look like this or something. But I hope you get the idea. So let's do this for f of 2. So we're going to substitute 2 for all of this. That becomes 1/4 2 to the power of 4. 2 to the power of 3. 2 squared plus 5. Just punching this all into a calculator. Four times 2 squared, that's 4 times 4, plus 5. This gives me 9. So the coordinate of this is 2, 9. As for the last one, once again, we're going to substitute x equals 4 into the original function to find the coordinates. So f of 4 is equal to, I'm just going to substitute this in, I'm not going to write it out, make it nice and easy for myself. Change this to 4, 4, oops. Oh no, let's try it again. 1/4 4 to the power of 4 minus 2 times 4 to the power of 3 plus 4 squared plus 5. This gives us 5. Once again, just hope you can understand that this function is not accurate, because apparently that is 4, 5. So the graph of this should actually look something like where this point here is 0, 5, that is 2, 9, that there is 4, 5. So I hope you've got an insight on the applications of the derivative. Hope to see you in the next video. Best of luck.